Welcome back. In this video I'm going to be explaining about numerical error. In the last video we talked about numerical approximations. Specifically we came up with a numerical approximation to the solution of a differential equation that modeled the velocity of a falling parachutist. So our differential equation was of the form dv dt was equal to the acceleration of gravity minus c over m times v, where c was the drag coefficient of our falling parachutist, m was the mass of the falling parachutist, and v was the velocity of the falling parachutist. And here I've just drawn a little plot showing a potential exact solution to this velocity, and then showing an approximation that could have been obtained by using a forward finite difference approximation to this derivative. And so I want to talk about the error that is associated with numerical approximations to this differential equation. So here we see that the numerical approximation doesn't fit exactly the exact solution, and in fact we could describe the error by measuring the distance between our numerical approximation and our exact solution, which would be these values right here. And so the way that we do that is and this error has a name, it's called the true error. So capital E subscript t is the way that we typically denote the true error. So this is called the true error, and it is equal to the true value. So the value of the exact solution, that's this value right here, the true value minus our approximation. Now in this case that value is going to be negative because our true value is less than our approximation in magnitude, so the error is going to be a negative value. But you could just as easily imagine the case where maybe our solution looked something like this, where we had our true value, or our exact solution maybe to some differential equation looked like this, and our numerical approximation looks something like this. And now our error is positive. So another important way in representing the error is to do percent error. And so the percent relative true error we denote with the symbol epsilon subscript t for true error. This is the percent relative true error. And that is equal to the true error just normalized or divided by the true value. True value. And that gives us a sense for how big the error is relative to the true value. Hold on a second here. Sorry, that was my janitor coming into, well, the janitor coming into our lab to change the trash can, so I paused it for a second. Anyways, so the percent relative true error is the true error divided by the true value times 100%. and that gives us a sense for how big the error is relative to the exact solution. Now, I talked about in the previous video how for most engineering problems in the real world, we don't actually know the exact solution. Exact solutions usually only come up for very simple and idealistic cases. So when we're doing some kind of solution, numerical solution for a problem that doesn't have an analytic solution, we actually can't compute the true error because we don't have the true values. And so correspondingly we can't compute the percent relative true error. So we need to have some way of approximating the error and estimating how big it is going to be. And so what we can do is we can define the approximate error. So I'm going to call this, denote it with capital E subscript A. That's going to be the approximate error. And the approximate error is simply defined as your current approximation minus your previous approximation. Now, current and previous, what do I mean by that? Well, typically when we are solving some mathematical model for some solution numerically, when we're using a numerical method, we use an iterative process. So maybe we approximate, we come up with one approximation, so I'm just going to call it approximation 1, and then we iterate again and we come up with a second approximation 2, and then we iterate again, we come up with a third approximation for some value that we're trying to compute. And we iterate. So first, our first approximation we generate probably depends on our initial condition, and our second approximation depends upon our first approximation, and so forth. And so this idea of iteration is very common in numerical methods. And so that's what I mean by a current approximation minus the previous approximation. So if I wanted to estimate the error at iteration 3, I would take my third approximation minus my second approximation. And that would be equal to my approximate error. Let me give you an example of this. Let me show you on my slides here. So in my velocity of the falling parachutist example, this is showing an example of the true error. So here I'm calculating the absolute values of the true error. So here I've got a table showing time t equals 0, 2, 4, 6, 8. Here's my approximate velocities, and here's the true value of the velocities from the true solution, and here's the true error and the true percent relative error. Now, getting to the approximate error. So here I'm showing the exponential function expanded in what's called a Taylor series. And so what we can do using Taylor series, we can actually show that this function, the exponential of x, is equal to some infinite series 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus a whole bunch of other terms, an infinite number of terms. Well, you can think of a first approximation as just being e to the x equals 1. So if we just use one term, so here I'm showing a table. I've got one term. The approximation is equal to 1 for e to the x for all values of x. And I can't compute an approximate error or a percent relative approximate error because I don't have any previous approximations. But as soon as I use two terms to calculate an approximation for e to the x, now I can say, okay, at x equals 0.5, I know that my approximation is equal to 1.5, and my approximate error is equal to the difference between these two, which is just 0.5. And then I can add a third term on, this x squared over 2 factorial, and I can see that evaluated at x equals 0.5, the approximation comes to 1.625. If I take the difference between this approximation and the previous approximation, I get this value for my approximate error. Now, I haven't written down the definition for the percent relative approximate error, but you can imagine it's defined just like the percent relative true error. So let's go back and go ahead and define that for you. Up here I've got the approximate error, and let's go ahead and just write down the definition for the percent relative approximate error, denoted epsilon with a subscript of a. This is equal to the percent relative approximate error. Approximate error. That's equal to the approximate error divided by our current approximation times 100%. All right. Now, the nice thing about error is once we've kind of explained it this way, we can actually quantify the error in terms of how bad it is. And for maybe some engineering design, we want to do some simulations and figure out how well that design performs. Well, when we compute, let's just remember the video of the chopper model being put through a computational fluid dynamics simulation. Well, all the properties, fluid properties that are computed are going to have an error associated with them. And let's say we want our design to be accurate to a certain error value. That will help us with our tolerances and help us know if our model even is a good model. So now we can quantify that using these terms, percent relative error and the actual error, both the true value and the approximate value. So you should know what true error is now. True error. And you should also know what approximate error is and how they're related to each other. Know what approximate error is. Alright, well that is going to conclude this video, and next video we're going to talk about the Taylor series.